Hello! In this video, we're going to prove the following theorem. The square root of 2 plus the square root of 2 plus the square root of 2 and so on until we have a total of n radicals, or n2's, is equal to 2 times the cosine of pi over 2 to the power of n plus 1. Now, a way that we can word the left-hand side of this equation more precisely is by defining the following sequence. We consider the sequence xn from n equals 1 to infinity, defined by x1 equals the square root of 2, and assuming we have defined xn to be a positive number, then xn plus 1 will be equal to the square root of 2 plus xn. So we have defined the sequence recursively. Well then, notice, in that case, x1 is the square root of 2, but then applying our recursive relationship, x2 is just the square root of 2 plus x1, which is equal to square root of 2 plus the square root of 2. If we do the same for x3, x3 is square root of 2 plus x2. So then let's substitute x2 for what it is. This is just square root of 2 plus the square root of 2 plus the square root of 2. That's it. As you can see, this pattern will continue. So that's how we can phrase what the left-hand side of this equation is saying more precisely. So what we're really going to prove here is we're going to prove for every positive integer n, xn is equal to 2 times the cosine of pi over 2 to the power of n plus 1. And we're going to prove this using induction. So let's start with the base case. In the base case, we're trying to prove that this is true in the case where n is equal to 1. So we want to prove that x1 is equal to 2 times the cosine of pi over 2 to the power of 1 plus 1. So let's write out the right-hand side where n is replaced with 1. Well, inside the argument, this is really just pi over 4. So we have 2 times the cosine of pi over 4. But then the cosine of pi over 4 is just equal to square root of 2 over 2. So we have 2 times the square root of 2 over 2. The 2's cancel out, and so we're just left with square root of 2. But x1 is equal to the square root of 2. So this is just x1. So we see that x1 is equal to 2 times the cosine of pi over 2 to the power of 1 plus 1. So we have shown that this equality is true in the case where n is equal to 1. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer n. And we assume that this equality is true for that arbitrary positive integer n. And the whole goal of the induction step is to show that this equality is also true for n plus 1. So we want to show that xn plus 1 is equal to 2 times the cosine of pi over 2 to the power of n plus 2. So let's see how we can show this. Well, first of all, let's write out the left-hand side. So we have xn plus 1. Well, by the recursive relationship, we know that xn plus 1 is equal to square root of 2 plus xn. And we know that xn, by our induction hypothesis, is equal to 2 times the cosine of pi over 2 to the power of n plus 1. So then let's factor out a 2. But now you're probably thinking, where do we go from here? Well, we want to bring cosine of pi over 2 to the power of n plus 2 into our work. And to do that, well, is there some sort of relationship between cosine of pi over 2 to the power of n plus 1 and cosine of pi over 2 to the power of n plus 2, notice the arguments differ by a factor of 2. So it might be useful if we use the double angle identity for cosine, which says the following. Well, there are actually a few double angle identities for cosine, but the one that's going to be useful is the one that expresses cosine of 2 theta in terms of cosine of theta, which is given by 2 cosine squared of theta minus 1. So this is true for every real number theta. Well, solving for cosine squared of theta, we get this. So this is true for every real number theta. Notice this looks kind of similar to what we have under the square root. And to convert this 1/2 to a 2, let's multiply 4 on both sides. So this is true for every real number theta. Now, these two values are equal, and since these guys are greater than or equal to 0, we can take the square root of both of them. So the square root of both of these guys are equal. Right? The reason why we took the square root is because we have a square root right here. But what do we have on the left-hand side? We could express that by breaking up the square roots like this. The square root of 4 is just 2. And what is the square root of cosine squared theta? Well, in general, the square root of a squared is equal to the absolute value of a. Right? This is true for every real number a. So we can apply that here. Square root of cosine squared theta is absolute value of cosine theta. So we get 2 absolute value of cosine theta. So what this chain of equality shows is that these guys are equal to each other for every real number theta. So we will apply theta to the real number pi over 2 to the power of n plus 2. So we have this. But actually, cosine of pi over 2 to the power of n plus 2 is positive, because the cosine of anything between negative pi over 2 and pi over 2 is positive, right? That's where the cosine function is above the x-axis. So we can get rid of the absolute values here. This is just 2 times the cosine of pi over 2 to the power of n plus 2. So we applied the double angle identity for cosine to obtain that this guy must be equal to 2 times the cosine of pi over 2 to the power of n plus 2. That's exactly what we wanted to arrive at. And so, we're done. We have shown that this is true. That's exactly what we did through this chain of equalities. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. So, by mathematical induction, we have proven for all positive integers n, this equality is true. And so this completes the proof. And so yeah, that's pretty much it for this video.